we're going to look at the energy stored on a capacitor. First of all, we have these two plates which basically make up what the capacitor is. The potential difference between the plates is equal to 12 volts. Now we move a negative charge from the positive plate to the negative plate, so we basically have to do work. So since the potential difference from one plate to the other is 12 volts, it means that for every coulomb of charge it takes 12 joules. So 12 joules are needed to transfer 1 coulomb from the positive plate to the negative plate. So the energy that coulomb gains in potential energy is 12 joules. The potential difference is equal to the energy per unit charge. Or you could say the energy is the potential difference times by the charge. So remember this, energy is equal to potential difference times by charge. The energy stored on the capacitor must be energy is equal to the potential difference times by the charge on the plates. True or false? Remember that energy is equal to the charge times by the voltage, or by the potential difference. You can say yes and no. The problem is the potential difference across the plates increases when the capacitor is still charging. The potential difference starts off with 0 volts and this increases to the maximum value, and the charge will always be equal to V times by C, but the V will be changing as the charge changes. And the graph looks like this. We have potential difference on the left on the y-axis and we have charge on the x-axis. But the interesting thing is, we know that the energy is the potential difference times by the charge, but it's changing all the time. So we find little strips and we find out the work done, or the energy, is the potential difference which is changing times by the charge which is changing. So the energy is the charge times by the potential difference at that time. In other words, it's the area under each strip. So in other words, it's the area under the total graph gives the total energy stored when we charge the plates. So in other words, since it's a triangle, the energy is the half times by V times by Q. But we know that for capacitor, Q is equal to VC. So we substitute for Q and we end up with energy is equal to half V times by VC. And this reduces to the energy in a capacitor is half CV squared. In the data booklet, this is the way we see this. Let's look at a question. This is the equation we need. Calculate the energy that can be stored on a 5000 microfarad capacitor when 25 volt potential difference is across its terminals. The energy is equal to half CV squared, is equal to 0.5 times by 5, because that's 5 microfarads, which is 5 times 10 to the negative 3, times by V squared, which is 25 squared. This gives an energy of 1.6 joules. The second one is a capacitor of value 100 millifarad stores an energy of 250 joules. Calculate the PD across the capacitor. And that gives a potential difference of 71 volts. So the summary. This is a graph of the potential difference against charge on the plates. The energy is equal to PD times by charge. However, in this case, we have the area is half of this area, which is a triangle. So it's half V times Q, but Q is equal to VC. Energy is equal to half V times by VC. So the energy is half CV squared. So this is basically the energy stored on a capacitor.